Hey, math people, for definite integrals, we have some fixed bounds. Let's find the area underneath all four of these curves. You need to know how to find the antiderivative, sure. But you also need to know a little bit of trig and, well, some tricks that'll help us out with simplifying certain expressions. Let's just get to it. Hey, we have a parabola here. Let's find the area of this parabola from -6 to -4. Way we do that with simple variable x is raised to a power. We add 1 to the power. So we're finding the antiderivative. We're going in the reverse direction of the derivative. With derivative, that'd be easy. You just swing this 2 up front. 2 times 2 is 4, and you lower this power by 1. But we're doing the reverse process of that. We're adding a power, or we're adding 1 to the power. And we need to think about what this coefficient should be if its derivative is 2. So you're essentially dividing out by the new power. So in which case we're dividing out by this new power of 3. Sure enough, if you take the derivative of 2/3 x cubed, yeah, you get 2 times x squared. So it's the reverse process of derivatives, yeah? Over here, we are continuing to add on the next term. It's now going to be x squared because we're adding 1 to this power. And we're dividing by 2. So, well, what was 1/16 divided by 2 is, well, now 8. 16 over 2 is 8. Right? Move that 2 up front. 2 times 8 is that 16. And we like constants with taking the derivative because the derivative of a constant is 0. In the reverse direction, we just tack on an x to the side. So this is plus 29x. And we're evaluating this from -6 to -4. Continuing this process, though, we're going to have a pretty long string here. What we want to do is we want to plug in -4 to this expression and then subtract off what would happen if we plug -6 into this expression. And this is due to our fan favorite theorem. Fundamental theorem of calculus allows us to perform this algebraic step here. So what I want to do is I want to take -4 and plug it into all these x's. So it's going to be 2/3 times -4 to the third, plus 8 times this -4, now to the second, plus 29 times -4. Okay, so that was the process of plugging in -4 to this expression. Now let's plug in -6. So minus, same exact thing that's going to happen, except I'm replacing all these -4s with now a -6. So 2/3 times -6 to the third, plus 8 times -6 to the second, plus 29 times -6. Yep, that's your final answer. You just have to kind of perform all this algebraic, or it's evaluation now of just numbers. There's no more algebra, really. What does this end up coming out to? So if you perform all these steps properly, I'm not going to sit here and think about, oh, okay, -4 to the third, that's -64, blah, blah, blah. So you should end up getting -2/3 from this. So this was -2/3. Now, I don't really mind all too much that I used up a lot of the space for this because this antiderivative is not too bad. One thing I recommend is that if you have a coefficient, always just to bring it out to the side because this is the same exact thing as -4 multiplied by the integral from 1 to 2 of 1 over x dx. This just kind of removes some of the clutter, allowing you to see the antiderivative a little bit more clearly because integral of this expression is just the natural log. So this is going to be -4, and we'll put it in brackets here, natural log of the absolute value of x from 1 to 2. Alright, so let's plug in 2 and let's plug in 1. This is going to be -4 times natural log of 2 minus natural log of 1. We know the natural log of 1. We can think of it this way. So natural log of 1, that is the same thing as log base e of 1. We can think of this as e to what power is equal to 1? Well, anything raised to the 0th power other than 0 is 1. So this actually just goes away. Natural log of 1 is 0. So now we just have -4 natural log 2, and some people are probably okay with writing it this way as your final answer. This is fine. You can also do some cool fancy tricks with it. You could bring this -4 as a power, so you can write this as natural log of 2 to the -4th, and 2 to the -4th, man, what is that? That should be 1/6. So natural log of 1/16. You could write it as natural log of 1/16. So that was a log property, which allowed me to bring a coefficient of a natural log up as a power to whatever you're taking the natural log expression of. And 2 to the -4th, okay, well, bring that 2 down below. 2 to the 4th is 16. So you could write it this way. I think all these representations would be just fine with me, in my opinion, and probably fine with most people. But I would say minimally, a teacher would want you to remove this natural log of 1. I think that's something you should know. Okay, that was not awful. Looking at this next one, these might get awful if you don't remember your unit circle. So again, I see this -2. Let's bring that up front to not really have to worry about it when we're taking that antiderivative. So this is going to be from -2 pi over 3 to -pi over 4 of cosecant square x dx. Sure, okay. What is this antiderivative? What is the antiderivative of cosecant square x? Okay, so we know that the derivative of tangent is secant square. Actually, thinking about this cosecant square x, I know the derivative of cotangent is negative cosecant square. So if anything, I kind of want to bring this negative back on in, so that way it kind of vanishes in the problem. Antiderivative of negative cosecant square is just cotangent. So with that said, I can just jump straight to 2 times the cotangent of x from -2/3 pi to -pi over 4. Yeah, derivative of cotangent x, negative cosecant square. So therefore, antiderivative of negative cosecant square is cotangent x. So now we have to know a little bit of unit circle stuff. Cotangent of pi over 4. So we like pi over 4. That's the case where both x and y are both the same value, √2 over 2, comma √2 over 2. It is negative pi over 4 though, so it is going to be, instead of √2 over 2 over √2 over 2, which is 1, one of them is negative, so the output is -1. So cotangent of negative pi over 4 is -1. Okay, is it going to be quite as easy with -2 pi over 3? Not quite. That one you have to maybe do a little bit of thinking on. Should be 1 over √3. So -1 minus 1 over √3. I guess we can clean this up a bit. Do I want to, though? Not really, is the answer to that. I guess I can. So I'm just going to make this 2 times negative √3 over √3 minus 1 over √3. Maybe one last step of simplification here. I'm going to have, I'll write it this way. I'll write it as -2 times √3 minus 1 all over √3. I'm just going to write it that way. Of course, you can write the decimal representation, which I think I have somewhere. I should have somewhere. Does that come out to -3.155? I sure hope it does. So it actually doesn't, I just checked, but that's because I just simply factored out a negative incorrectly. I had this negative plucked out here, because these are both negative terms, so I factored out a negative, so an easy fix. And that is one way of representing your final answer. Looking at this guy, this appears to be a tricky antiderivative if you don't happen to know all your derivative rules. Because if you do know all your derivative rules, this is the easiest one of the bunch. The antiderivative of this thing is just arc sine. This is a derivative of arc sine, or inverse sine, you may prefer, I guess. All right, so this is equal to arc sine of x from root 2 over 2 to root 3 over 2. So I guess we can plug those in. Yeah, we can do that. So I kind of skipped that middle step here in that process, but here I'll show it. It's going to be arc sine of root 3 over 2 minus arc sine of root 2 over 2. All right, we're pretty much done here. We just need to know the arc sine of root 3 over 2 and the arc sine of root 2 over 2. Let's think about arc sine for a moment. Sine is the y value, so when do we have a y value of root 3 over 2 in a unit circle? That occurs on pi over 3. And this one's a little bit easier. At least I like the root 2 over 2 case. So when do we have a y value of root 2 over 2? Well, that's the simplest case. That's the first quarter, so it's pi over 4. Okay, a third minus a fourth is a 12th, and we're done. That's pi over 12. You can make like denominators if you want, but you can also just know a third minus a fourth is a 12th. Yeah, that's it. So definite integrals, a little bit of a different conversation to all these pieces. If you are provided bounds, the answer is a number. If you are not provided bounds, you just need to write the antiderivative, and of course, naturally, the plus c in that case. Here, we didn't play around with the plus c because these are all definite. I have an a value, I have a b value. I'm saying, hey, find the area between these points. It is a number. Areas are numbers, just so you know. Average value. So imagine you have some sort of curve. And in this curve, you got a lot of really skinny people. So you got this skinny person, and you got this skinny person, and you got this skinny person. However, there's no gaps in between all these skinny people. And there's infinitely many of these skinny people. So these are all people, they're all standing, these are heads that I'm drawing, and they're just kind of doing one of these things. All I'm trying to say is, of these infinitely many skinny people that are infinitely stacked next to each other, what's the average height? That's it. So I mean, you can think about it more contextually of just line up 6 people, find the average height of the 6 people. That's a little bit more like conceptually digestible. But with a function, it's continuous, so technically these rectangles don't exist as rectangles. These people don't exist as rectangles. They exist as infinitely small slivers of rectangles. It's kind of the idea of integration, Riemann integration in the first place. So where's the average height? Who has the average height in this line? That's the idea behind this. So here's the formula for that. It's really just an averaging formula. You integrate it, which is the area under the curve, and you multiply by 1 over the length of the interval. And that's how you find average. All right, so let's look at the first one. So we are a parabola from, and we want to find the average value from 2 to 3 on this parabola. Okay, this one's just easy to draw. I'll draw this one. I don't feel like drawing that one, but I'll draw this one. It's just scooted up 1 unit, and it's a pretty wide parabola. Okay, and then from 2 to 3, we'll say that right here. So where's the average height on this interval? I don't know, probably somewhere like right there. Let's try to figure out what it is. So average. It's going to be 1 minus b, or 1 over b minus a. Here my b value is 3 and my a value is 2. So it'll be 1 over 3 minus 2. That's just 1, so actually that just goes away, which is nice in this case. And we're integrating this expression, x squared over 2 plus 1, and tack on that dx. So this is just 1, actually. I don't have to worry about this. I just have to integrate this expression. This only happens when you have an interval length that's exactly 1. So here, this interval length is 2, and that won't happen. We're going to be cutting in half here. All right, so antiderivative of this is x cubed over 6, right? Bring that 3 up front, 3 over 6 is a half, yep. And then antiderivative of x is, of 1 is just x. Something I forgot. Bounds are provided. So here I should have done 2 to 3. So let's just find the area of this thing from 2 to 3. Okay. Plug in 3. 3 cubed over 6 plus 3, and then plug in 2. We're subtracting that off, sorry. So it'd be 2 to the third over 6, and then plus 2. So whatever that comes out to, that will be your average value. If we consider this, before we get to the answer, think about this a little bit conceptually. If I plug in a 2 to this expression, that would be 4 over 2, that's 2, 3. So the leftmost guy has a height of 3 in this little analogy here. If I plug in a 3, so I'm going to say this output hat is 3. It's a height of 3 feet, I guess. If I plug in 3, 3 squared is 9. 9 over 2 is 4.5. This is 5.5. However, it's not a perfectly linear line. It's tempting to say, oh, well, what's perfectly in between 3 and 5.5? What is perfectly between those values? 4.25? It's tempting to say, oh, okay, well, the middle height's going to be 4.25. Not 100% true. These aren't going up in a perfect linear fashion. 4.25 should be roughly the answer. It should be pretty close to that. It's not going to be exactly 4.25. This does not go up in a perfect linear trend. It's got this curvature to it. So with that said, it should be reasonable to expect an answer around 4. Let's see what it actually is. I don't feel like doing this calculation. Have it somewhere. 25 over 6, which is roughly 4.167. So not quite 4.25 because we have that little bit of a curvature to it. Right. Okay. Looking at the next one. So, same story. This time around, we're not going to worry about drawing the graph, though. The average is equal to, let's just use the formula, 1 over b minus a. So it's going to be 1 over negative 2 minus negative 4. And then we're integrating this curve, negative 1 over x squared dx, from, and I won't forget the bounds this time, negative 2 to negative 4. Man, there's a lot of negatives here. The nice thing about this denominator is that these negatives will go away. It'll turn to just half for this constant term up front. What is the antiderivative of negative 1 over x squared? So this is the same thing as negative x to the negative second. So just like how over here we added 1 to the power of x, it's the same story here. We're adding 1 to the power of x. If we add 1 to negative 2, that's going to be negative 1. So this will have a power to negative 1. And if we were to have brought this up front, it would just be negative. So we're dividing by a negative here. But we had a negative up front. So it's just going to be 1 over x as your antiderivative, right? So derivative of x to the negative 1. Bring the negative up front. It's now negative x to the power of negative 2, which is what we have here. This is my antiderivative. That's actually pretty nice. That's actually, I guess, one people recommend knowing, by the way, that d dx of 1 over x, this is equal to negative 1 over x squared, right? Yeah. People recommend knowing this one on your list of things to know, and the square root of x. Like, those are like nice to know or nice to memorize ones, but you can actually just do it on the spot too. It's up to you, your call. You do you. So we now have negative, actually the negative goes away, 1 over x from negative 2 to negative 4. Really easy to either accidentally add a negative or take out a negative. So don't do that. All right, half times a negative fourth minus a negative half. This is a positive half, and this is a normal negative fourth, so that's going to be a fourth here. Half times a fourth is an eighth. Fun fraction play at the end. Okay, that's average value. Please continue to math on. I will do the same. See you in the next video.